Okay then, good morning everyone, once again. Any questions before we begin? Okay. So we're going to continue on with our Fourier series. We don't have too much left to do with this. So a few more lectures to finish off this chapter. Maybe I'll give a lecture or two, giving some extra stuff that isn't in the notes and linking back to Laplace transforms a little bit, perhaps. But we're nearly there, so we should comfortably finish the material by the end of this term. And then there's 2 teaching weeks after the Easter break, so we can make good use of those for kind of exam preparation and looking at past exam papers and so on. Okay? So continuing with our Fourier series material, so just remember what we're dealing with is, like at the top of the screen there on equation 3.1, we're dealing with objects like this, which are Fourier series. Okay? Functions. So for well-behaved functions, periodic functions, period 2 pi, although in general we can stretch out that basic interval from minus pi to pi to really any interval at all, using some kind of rescaling. So we're dealing with this, so we think of this as it's somehow similar to maybe like a Taylor series for a function, expanding a function as an infinite polynomial. Well, this is a variant on that. Said this time we're expanding a function not as an infinite series of polynomial functions or polynomial terms, but in terms of these basic sine and cosine functions. And this family of sine and cosine functions, together with the constant function 1, this family down here at the bottom of page 59, we can give this a kind of linear algebra interpretation, because this family of functions is a basis for the vector space of functions which have Fourier series. Okay? And this family, it's a nice enough basis. It's not a perfect basis. The best kind of basis you would have is a orthonormal basis, a basis of orthogonal basis vectors, all of which have length 1. The way we've set things up here, this isn't quite orthonormal basis, but it is orthogonal. So all these functions here are mutually orthogonal. They're all orthogonal to each other. What does orthogonal mean? Well, normally, okay, geometrically, we kind of think of that as meaning that the vectors are perpendicular to one another. In this context, it means, well, we don't have a strict geometric interpretation, but we do have this inner product, the standard inner product on function spaces like this over the interval minus pi to pi. So the standard inner product is just the continuous analog of the discrete dot product. So instead of multiplying together corresponding coefficients of vectors and adding up those products, we multiply together corresponding values of the functions, and we integrate. Integration is the continuous version of summation. We integrate those products across the interval minus pi to pi. And saying the family of functions is orthogonal means that when you take 2 different functions from f, phi and psi, so phi could be one of your cosines, psi could be one of your sines, etc. Take 2 different functions, then they have inner product equal to 0. Now, of course, in the Fourier series, okay, so remember not to fall into the trap of giving previous lectures again, with the review. So the question of finding a Fourier series is the question of finding these coefficients, an and bn, and the constant coefficient a0. Okay? So to end the recap, those we found last time that those Fourier coefficients come to us via these formula here. So these are all inner product formula. So the constant coefficient is the inner product of our objective function f with the constant function. The an's are all the inner product of our objective function f with the corresponding cosine function, or as written there, the integral of f times the cosine function, and a similar thing for the coefficients bn. Okay. Now last time we looked at some examples. We looked at finding Fourier series for the square wave function and for the function f of x equals x and so on. So before we look at other particular examples, we're going to look at section 3.3 here, which is on page 63. And this is to do with a kind of simplification of Fourier series when the function you're examining, the function f you're examining, when it has certain properties. Okay. So this is a simplification for the Fourier series of an odd or even function. In case you haven't met it before or you've forgotten, we're going to review here what an odd or even function is. Okay? So it's a simplification for the Fourier series of an odd or even function. Okay, so definition of odd or even first. Well, so a function f is even what that means is for every x in the domain of the function, f of x is equal to f of minus x. So if you throw in as an argument to the function plus 5 and minus 5, the function gives you the same answer back. Okay? So it only depends really on the absolute value of the argument. It doesn't care about the positive or negative sign. A function f is odd means for every x in the domain of the function, f of minus x is minus f of x. So this time, the function is taking account of the sign of the argument. Okay? And the function works so that it supplies values of opposite sign on the arguments x and minus x. So if you throw it 5 and minus 5, the function gives you back different values on 5 and minus 5, and one of the values is the negative of, or each value is the negative of the other one. Okay. So this is the kind of formal definition of odd or even as terms for functions. So obviously you have to not get this confused with odd or even integers, things being divisible by 2, and it's not directly related to that, it's just a different use of the word. So these have nice interpretations, or nice interpretations on the graphs of functions. Because let's think of an even function. Well, okay, let's just think of some kind of generic graph of a random even function. Okay. Well, on the positive half of the domain, for positive arguments, here's just a random squiggly line. But if this function is even, it has to have exactly the same behavior on the negative arguments. So the graph on the negative side, do this in a different color, has to be the exact mirror image. I'll attempt to draw that here. Exact mirror image of what we see on the positive side. Yeah, that's a pretty good drawing. So the function, when you reflect it in the y-axis, its two halves mirror each other. Okay, because when you evaluate f on x, you get some particular value, and when you evaluate f on minus x, which would be down here, more or less roughly right, you get exactly the same value. Yeah? F of x equals f of minus x. So that's the typical look of an even function, whereas an odd function, the typical look of it, probably made my thing a little bit too complicated, but okay, there's my generic squiggly line again. But if this function is odd, it doesn't have the same behavior on the negative half of the domain. It has exactly, well, the same behavior, but you reverse the sign. Okay? So what goes up and wiggles around up here has to come down and wiggle around down here. And then go whoop. Yeah. And then come down again and go whoop. Something like that. Okay. So this time it's still symmetric, but not under simple reflection in the y-axis. You have to reflect it in the y-axis and the x-axis. When you take this plot, this graph, reflect it in both axes, one after the other, then it's a mirror image. Then it's symmetrical under the composition of those two reflections. Okay. So here, like, take a typical value x here. It has a certain value. When you take the value on negative x, which would be here, you get the value of the same. The value of the function is the same magnitude, but opposite sign. Okay. So those are odd and even functions. And yeah, so why are we introducing these when we're talking about Fourier series? Well, it has to do with integrals. So first of all, let's make the observation about what happens when we integrate these functions from minus pi to pi. So let's say minus pi is down here, plus pi is up here. So we've got minus pi down here, plus pi up here. What's going to happen when we integrate these functions across the interval minus pi to pi? Well, remember, the integral is keeping track of the signed area between the curve and the x-axis. So portions above the horizontal, above the x-axis get counted with the positive contribution. Areas below the negative, below the x-axis contribute a negative area to that sum. So when you integrate it on the positive half from 0 to pi, you get a certain value. But when you integrate it on the negative half of the domain, well, you get exactly the same contribution again. So you get some kind of signed area, a largish positive area, subtracting this smallish negative area. We get exactly the same contribution on the left-hand side. So you can say for this function here, the integral from minus pi to pi of an even function, f of x dx, we can simplify that somewhat and say it's twice the integral over the positive half of the domain. Okay. We can just kind of formulate this result just by looking at the graph. We'll prove it formally in a moment, but seems pretty clear just from that sketch. But what happens here for the odd function, okay, you integrate it over the positive half of the interval from 0 to pi, you get that kind of contribution. But when you integrate it over the negative half, well, you get the same components, you get the same kind of component areas that you're getting with the integral, but they all carry opposite sign. So this area here was counted with a positive sign in the integral, but this region here, which is supposed, okay, this sketch is a bit off, but this is supposed to be of exactly the same area as this one up here, but it's below the line, so it gets counted with a negative sign. So the two cancel out in the integral. Similarly, this negative piece of area here, when you integrate over the positive half, has its sibling over here, which has the opposite sign, which is positive. So those two parts cancel each other out. So when you take an odd function and you integrate it from minus pi to pi, and of course there's nothing special about pi here, just we're integrating it across an interval centered at the origin. That's the key point. When the interval of integration is centered at the origin, and the function is odd, the two sides are going to cancel out. Okay? Every bit of area on the right-hand side has its corresponding bit of area on the left-hand side, which is the opposite sign in the integral. Okay. So this nice behavior of odd and even functions, when you integrate them across intervals centered at the origin, this is going to have consequences for their Fourier series. Okay? But of course, okay, if we consider this f to be the objective function, the function that we might be finding the Fourier series of, well, we only integrate f alone when we're working out the constant coefficient, a0 in the Fourier series. For the other coefficients, for the a_n's and the b_n's, we have to integrate the product of this objective function f with either the corresponding cosine function or the corresponding sine function. So how does all this odd and even stuff relate to the sine and cosine functions? Are sine and cosine odd or even? Well, cosine function has this property that it's even. Okay? For every real number x, cosine is, you draw the graph of the cosine function, you notice it's exactly symmetrical under reflection of the y-axis. And sine is an odd function. The graph of cosine goes something like this. It's just reflected in the y-axis. The graph of sine, you have to reflect it in both axes. Okay, so cosine is even, and sine is odd. Okay, well that's nice. So our basis functions fit into this picture very well. Of course, the constant function 1 being a constant everywhere, that's an even function as well. So maybe we have a few things to do. We want to understand what happens to odd and even functions when you multiply them together. Take two even functions, multiply them together, take two odd functions, or take an even function and an odd function, multiply together. Because we want to understand how the products between f and one of the cosines and the sines are going to behave. So we want to understand that. We want to formally prove these integral results, about the integral of an even function and the integral of an odd function. I mean, the pictures are pretty convincing. The pictures and arguing about the signed areas is more or less the proof, but maybe we'd like to see a formal treatment of it as well, one that just follows from the formal definition of odd and even functions. So which order will we take these in? Maybe let's look at the products first. So let's understand the products. So that's theorem 3.2, isn't it? Any questions before we proceed? Any question about the definition or the observations we've made so far? Anything you'd like me to clarify? Okay, so theorem 3.2, we want to understand these products. And you can see the result there. The product of two evens is even. The product of two odds is even. And the product of an even and an odd is odd. Okay. So we want to let u1 and u2 be two even functions. And v1, v2 be two odd functions. So let's prove these properties. So for every value of x, if you take one of these, if you take the product function u1 times u2, so that's the product of two even functions. So what do you get when you evaluate it at minus x? Well, by definition of, so first of all, we applied the definition for what multiplying two functions together means. Yeah? So product function u1 times u2 evaluated at minus x is, of course, the product of the individual values. That's just the definition of product for functions. Well, then it's clear what to do. Then we can use the fact that u1 and u2 are even. So u1 and u2 both take the same value on plus or minus x. They don't care whether you give them plus x or minus x as an argument. They return the same value because they're both even functions. And of course, that is the same as the product function u1, u2 evaluated at x. Kind of apply the definition of the product function again, we get u1, u2 evaluated at x. So that line was since u1, u2 are even, and this is the definition of product again. So from beginning to end, look what you have. You have for every x in the domain of these functions, when you evaluate the product on negative x, you get the same values when you evaluate it on positive x. Okay? So therefore, the product function u1, u2 is an even function. The other properties can be proved in just exactly the same way. Exactly the same principle. Just form the product, evaluate it at minus x, apply the definition of whether they're even or odd, and just look at the resulting sign that comes out. Okay? So similarly, let's take v1 and times v2 and evaluate that at minus x. Well, by the definition of product, so we'll move slightly quicker now. By the definition of product, that's just v1 of minus x times v2 of minus x. But both these functions are odd, so this gives us minus v1 of x times minus v2 of x. Okay, because v1 and v2 are odd. You got two negative signs there, so they cancel out or combine together to give just a plus sign. So actually what you're looking at is v1 times v2 evaluated at x. So this product function v1, v2 is even. So you give it minus x and give it x, and it gives you the same value. Okay? So you've got corresponding justifications there. We're using the definition of the product function, and this here is since the vi are odd. v1 and v2 are odd. So therefore, when you multiply together two odd functions, you get an even function. Agreed? Now this is the drawback of using the, or potential drawback of using this odd and even terminology, because if you're using odd and even to refer to divisibility by 2, well, we know if you multiply an odd integer by an odd integer, of course, the product is odd. So odd times odd equals odd when you're talking about the parity of integers, whether they're odd or even, whereas when the terms are used as applied to the behavior of functions, you multiply together two odd functions, you get an even function. So the properties don't mirror each other. Okay? So it's potentially confusing, but this is the way the world is. Okay? And of course, the last property is when you multiply even times odd function, you get an odd function. Whereas with integers, you know, if you multiply an even integer by an odd integer, the product is even. So it's confusing. So you just have to remember that they don't behave the same. The two sets of terms when under multiplication don't behave the same, so just don't, you know, always think twice about it. Okay? So finally, if we consider the product u1 times v1, so we take an odd function and an even function, evaluated at minus x. Of course, by the definition of product, it's just product of the individual values. But then u1 is even, so this is u1 of x. v1 is odd, so this is minus v1 of x. So in total there we got minus u1, u2, sorry, that minus u1 times v1 evaluated at x. So the product function here is odd. u1 times v1 is odd. That makes sense? So just it's a nice application of the definition of function, product of functions, and just keeping track of your minus signs and applying the definition of odd and even. Is that okay? Any questions about that? So that's theorem 3.2. So we understand if we're given odd and even functions, what their products are going to be. So when we're defining the Fourier series of an even or odd function f, we'll know whether when the products that we're dealing with, f times cosine or f times sine, we'll know whether those are odd or even. Okay, so that's theorem 3.2. So let's go on to theorem 3.3 now, which deals with the integration results, which we've sketched out. So theorem 3.3 is just the result that I described just by talking about the look of the graphs, right? And that argument is correct, talking about the look of the graphs, but it's a little bit vague and hand wavy. Anytime you're trying to prove something by saying, this is just a squiggle of a graph. Of course, there's an infinite number of ways the graph could look. Am I absolutely sure that my reasoning about positive and negative bits is completely secure? Well, yeah, I am pretty much, but maybe just to get a formal proof down, maybe what we'd like to do is just base the integral, try and integrate this function f, and assuming it's even or assuming it's odd, try and get out these results about the integral. Okay? Just working from this definition alone. Not that that is necessarily better than the graphical observations here, but the two together, this kind of intuitive graphical observation for the proof, together with the secure, rigorous formal proof, working from the definitions and the properties of integration, the two together gives us a very thorough treatment of these results. Okay? It's a good exercise in working with proofs as well, because very often we see intuitively why a result might be true, or looking at some typical examples, we can observe that an interesting result might be true. But it can be a bit tricky sometimes to get it rigorously, formally down in good mathematical argument. Okay? But that's what we'll do here. So let's do the one about even functions first of all. So it's called g in the statement of the notes, so I'll use g. So we'll let g be an even function, i.e. g of x is always the same as g of minus x. This is for every x in the domain of the function g. Now we want to show that when you integrate it, we want to integrate g across an interval centered at the origin, so going from minus t to t. And we want to prove that this is 2 times the integral from 0 to t. I think we can prove it directly just by building a chain of equations. But yeah, so we'll start with this on the left, and we'll hopefully get this to 2 times the positive one. So the first property I'm going to use is the fact that we're allowed to split the region of integration up. So I can integrate the function on the negative half, integrate it on the positive half, and add the two integrals together. Okay? That's a basic property of integration. You can split the interval of integration up into disjoint subsets and integrate them individually and then add them together. Okay, and then now what I'm going to do is, well, let's leave the second integral alone, and then let's just work on the first one and make it look exactly like the second. And then we'll have 2 times the integral over the positive. Okay. So we'll leave that alone in the equation and just work on this one and convert it into that one. And I think in order to do this, we'll need we use a we'll use a substitution. Substitution. I'm going to replace x with minus t in the first integral. So when we do that, what we see is, yes, dx is equal to minus dt. When sorry, that's minus t there, isn't it? That's good. My world was falling apart there because I could see it wasn't going to work, but I'd forgotten this minus sign. Minus t up to 0. So when x takes on the value minus capital T, little t, of course, takes on the value plus t. And when x takes on the value 0, little t is, of course, 0. And so I have to replace x with minus t, so this is g of minus little t. And dx here is equal to minus dt, so I get minus dt. And the second integral remains unchanged. So now I've got a few minus signs here, and I've got the limits in the wrong place, so I just want to just see how that all works out. Of course, the function is even, so I can get rid of the minus sign in here. So that's since g is even. Okay, that's good. I've used the fact that g is even. When you make assumptions and proofs and you're trying to derive something from a property, and by doing some algebraic manipulation or something so on, you want to make sure that you actually use the assumption somewhere, make use of it. So I've used the fact that g is even here to replace g of minus t with g of t. And now I'll use this property that if you're integrating an integral from something to something else, you can change the direction of integration. Instead, integrate in the opposite direction, and that changes the sign of the integral. So if instead of integrating from t down to 0, I instead start at 0 and integrate up to capital T, that changes the sign of the integral. So there I'm using just this general property that integral a to b of anything is minus the integral from b to a of the same thing. Okay? Now up here it was minus t to 0, but you see then I changed the variable of integration here. I translated this from x into t. So you see here, at this lower limit, x is the value minus t. But when x is minus t, little t is plus t. Yeah? So when you're substituting for a variable in an integral, you have to transform, anywhere you see the variable in the integrand, you have to translate the differential. You also have to transform the limits of integration. Yeah. So this integral began at little x equal to minus t. So the equivalent thing is to begin this integral at little t equals plus t, because the relationship is little x and little t have the opposite sign. Okay? And now you can see what's happening. These two minus signs I have here, of course, are going to cancel out. Integration is linear, so this factor of -1 here can move outside. It's got minus. So this is the integral 0 to t, g of t dt, plus the integral from 0 to t of g of x dx. So that's using the linearity of integration. So this minus sign here, move outside and cancel with that. Now, are we nearly there? Well, yeah, we look at these two integrals. Now, they look kind of different because one is in terms of t and the other one is in terms of x. But you have to remember, the variable used for an integration means nothing. You know, when you're integrating a function, you're summing up the values of the function across a certain interval. Whether you temporarily call the variable little t or little x makes no difference whatsoever. The integral is only defined by the function g and where you're integrating. These two integrals integrate the same function g, and they integrate it across exactly the same domain, 0 to capital T. So this is simply 2 times the same integral. Remember, the variable that's used in integration, it doesn't mean anything. It's called x here, it's called little t there. I could call the variable Killian if I wanted to, g of Killian, d Killian. It's just a label for a real number. Yeah. X has no inherent meaning. It's just simply a label. What does have inherent meaning is the object we're integrating, this function g, and what domain we're integrating it over. And both times we're integrating the same function across the domain 0 to capital T. So this is 2 times. This is exactly the result we want. Integrating our even function across an interval centered on the origin, we get exactly out 2 times the integral over the positive half of the domain. Okay? So that's exactly kind of a formal rigorous version, working only from the definition of even and using the properties of integration, just a formal version of this kind of intuitive graphical argument that we had up here. And we can do a very similar thing for the other one. So we can prove the result about odd functions in a very similar way. Okay. So this time we're letting, so it's called h is an odd function in the notes. So we let h be odd, i.e. what that means is for every x in the domain, h of minus x equals minus h of x. Well, do I really need to write it out again? Really, it's going to be exactly the same as what I've written here for g. Because what I was doing there with g was just using properties of integration. There's only one place I used the fact that g was even, and that was in this line. And there, when I was using the fact that g was even, I moved from g of minus t, well, that's exactly the same as g of t. Now, if I redo that exact same argument, except this time using an odd function, h, in the place of g, everything will be the same, except when I move from h of minus t here, I have to move to minus h of t. The function is odd. So h evaluated at minus t gives me minus h of t. So I'll have 2 minus signs in front here, which will cancel with each other. So I'll get down to here, I'll have minus this integral plus the same integral. And there you see the 2 integrals will cancel. So really just replay the previous argument, and h being odd introduces an extra minus sign at line, so let's label this one here, star. When the function h is odd, we get an extra minus sign popping up here, so which changes the sign of that first integral. We get an extra sign at line star in the first integral. So instead of having this integral here plus the same integral again, we're going to have this integral here minus the same integral again. So the two are going to cancel out. So save us some time by just describing that. Replay our previous argument. H being odd introduces an extra minus sign at line star in the first integral. So the two integrals cancel out. Cancel to give 0. Big fat 0 for the integral of function h across the interval essentially. Is that okay? We're being a bit economical there, but for good reason, because this proof is really just exactly the same as that, with one extra minus sign popped in. Okay. And that kind of makes sense, because we're just using properties of integration. On the one hand, first time g was even, second time g was odd, so essentially the same argument. So now we've got two other theorems there, 3.4 and 3.5, but they really don't need any more proof other than just putting together these properties we've proved already. Okay. Everybody happy with that? That's there at the moment. Any questions about it or clarification I could give? Okay. So let's just look at the notes on page 64 there. So two theorems here, theorem 3.4 and 3.5, one about even functions, one about odd functions, and really it's just putting together what we know. And so in the first one, suppose g is an even function. Well, when g is even, think of where the coefficients bn come from. The coefficients bn come from integrating g multiplied by one of the sine functions. Okay, but sine is odd. G here in theorem 3.4 is even. So g multiplied by the sine function in total is odd. So the integral of it will be 0. So you always get 0 for the coefficients bn. So that means in this Fourier series here, there are no sine functions, because the coefficient bn is always 0. You're just left with the coefficients a0 and an. And if you want, you can provide the alternative definition for the an coefficient as being 2 times the integral over the positive half. This isn't so crucial here, but the main observation, the main result is that we just get a cosine series. So that object in 3.21 there, we call a cosine series. It's a series of functions, but we only see the cosine functions. And we're kind of making a constant function be an honorary cosine for that purposes. It's cosine of 0 times x. On the other hand, if your objective function is odd, so theorem 3.5 here, h is odd, well, now we think of where the a coefficients came from. The a coefficients come from integrating the function h multiplied by a cosine. But now h is odd, cosine is even. You multiply an odd function by an even function, you get an odd function again. Is this odd or even is about plus and minus signs? So in the a coefficients, we're always integrating an odd function. So those integrals will always come out as 0. We just proved that. Whenever you integrate an odd function across 0, an interval centered at 0, you get 0. So there's the A, for this odd function h, its A coefficients are all 0, so we don't see any constant function here in the Fourier series, and we don't see any cosine functions. The Fourier series has to just consist of the sine functions. Okay, so that Fourier series will be called a sine series. It's just a series assembled out of sine function. So, you know, you should write out those proofs yourself. You should make notes on those proofs yourself, but it's just putting together all the previous results for this situation. Okay? So this is some facts about Fourier series which we're free to use now. Whenever we're trying to find a Fourier series of a certain function, if we recognize that the objective function is either odd or even, it means straight away we know what the resulting Fourier series is going to look like. It's either going to be a cosine series for an even function or a sine series for an odd function. So it kind of cuts the amount of work in half, more or less. Okay, we better leave it there for the moment, but I'll leave you to read through section 3.4 yourselves. So have a read through section 3.4, and then for the upcoming tutorials, well, it might be a bit too soon for you for this morning's tutorial, but for Friday's tutorials or next week's Monday tutorial, we'll have exercises 3.2 available to us as well. Okay, thanks a lot. I'll see you later.